Graphs are our way of taking an algebra concept or a function when you get into talking about functions in pre-calculus. It's a way to take these mathematical entities and make them visual. Pictures are worth 1,000 words, and if you're like me, having a picture to represent something or illustrate something really helps me to understand that something. That's kind of my visual, I have this visual learning preference for that reason. If I can draw a picture of it, then I really know that I've understood it. And so our task is going to be to figure out how to connect the sort of formulas that we can use to represent a mathematical object, like y equals 4/3 x here. Connect that formula, which formulas, let's face it, are not the way that human brains are wired to think. Even mathematicians don't tend to think in formulas. We use them to communicate, we use them to calculate, but we don't use them to really understand. We tend to reach for other modes of understanding like graphs, or maybe tables of data, or maybe verbal descriptions or something, to help us to understand what something really is, sort of what is its essence. And you'll be doing a lot of that, especially next semester in pre-calculus. The graphs really start to ramp up because it's our best way to understand the relationship which is suggested, for example, by an equation with two variables in it. So let's take this first example where we have the equation y equals 4/3 times x. And I just want to ask you, if your task is to graph this line on this graph paper, what were your approaches? What did you try? What did you start doing? What came to mind? Make it a free association exercise. What do you know about what this question is asking you to do? So one of the options is, if we're thinking about a line, if I want to understand what a line looks like, all I really need to do is find the locations of even just 2 points on the graph paper. As soon as I have any 2 points on that line, then it turns out, a famous mathematician named Euclid figured this out about 2,000 years ago, 2 points uniquely determine a line that goes through them. So as soon as I have 2 points, all I have to do is place my ruler down on the paper, trace a line through those 2 points, and I'm done. So let's narrow down the task. We're going to reimagine what the task is asking us to do here. And we're going to make our new task to plot just 2 points. That's all we have to find. Okay, so how do I find 2 points that belong on this line? Yeah. So each point, we call it an ordered pair, okay, because it's going to have an x coordinate and it's going to have a y coordinate, and those two numbers together are going to determine where I place the point on this graph. And the relationship between the numbers in the first and the second coordinate, this relationship is governed by that equation. Relationship is governed by the equation y equals 4/3 x. But the thing is, if I want to plug something into this formula, what do I plug? And where should I plug it? Because there's a relationship between the numbers in the two columns here, the x's and the y's, we don't get to pick what goes in both columns, but we could pick what goes in one of them. If I choose a value for x, then you should be able to tell me what the right value for y is that goes with that x. For example, if I pick x equals let's say I pick x equals 9 or something, then you should be able to somehow tell me what y belongs with that value of x, because the relationship between them is spelled out by this equation. Likewise, if you pick a value for y, -3, then I should be able to, using that same relationship, tell you what the value is for x that goes with that value for y. So the key is we get to pick one independently. Get to be whatever we want. If we want to pick x, that's fine. Pick an x. Pick it. Be very specific. Be concrete. Pick a number. Put it in that column. Then the work is to figure out, based on this equation, what y matches with that x. Or if you did it the other way, what x matches with the y that you chose. But the whole process doesn't get started until you pick something. Right? You start the snowball rolling down the hill by picking a value for x or picking a value for y. So somebody who worked on this problem, if you picked a value for x, what kind of values for x did you choose? That's the other good news about this. Because you have a choice, you can make that choice so as to make it easy on yourself. One of the ways to do that is not to pick gigantic numbers for x that are going to make the arithmetic a challenge, but pick some reasonably easy to work with numbers for x. What's the easiest number to work with, do you think?
0.
Yeah, 0 is always a good choice. Anytime you can start with that, that'll at least get our ball rolling, right? If I pick the value 0 for x, then how do I know what the value for y is that's going to match up with x equals 0? How do I find it? Well, we know that the relationship between these two numbers, x and y, is governed by the equation y equals 4/3 x. So, if I'm picking 0 as my x value, what should I do to find the right y value that matches up with it? Yeah, this is where the plugging in comes in, right? If I choose 0 for x, then that is saying, let's replace the x in this equation with 0. Which, again, anytime we replace a variable by a value, use that empty skeleton of parentheses. But now I have on the right-hand side of my equation an arithmetic problem. 4/3 times 0. Luckily for us, we don't have to know a lot about how fractions work to answer the question, what is 4/3 times 0 going to be? 0. Because anything times 0 is 0. Yeah, exactly. So we don't have to know a lot about fractions to do that. Okay, great. So if x is equal to 0, then y must be equal to, in turn, 0. And that gives us 1 point on this coordinate system. How do I find this point? Where does the point 0, 0 live?
Where the x and the y cross.
Exactly. That's almost by definition. Yeah, where the x-axis and y-axis intersect one another, we call that the origin, by the way, because it's where our coordinate system originates. That's the point 0, 0. So now we have 1 point on our line. And whatever else I draw on this graph diagram here in the middle, however else I draw my line needs to at least, at minimum, go through this point. So that's the one thing that we know now. But 1 point is not enough to determine a line. We're going to need a second. So unfortunately for us, sitting and playing with zeros is only going to get us this far. To get us to the next step, we're going to need to pick a value that's not 0. Either pick it for x or pick it for y. I think it's more common. People tend to like to choose x values and then use the x's to determine the y's, mainly because it's going to require only arithmetic of us and not algebra, because the y in this equation is already sitting by itself. So if I pick a value for x, all I have to do is some arithmetic on this right-hand side. I don't have to solve for y. I just have to carry out the arithmetic. So somebody who did this problem, what other value besides 0 did you choose for x that made your life kind of easy? 1? Okay. So we can choose 1. That's another good choice for a small number that's easy to do arithmetic with. Right? So if I pick a 1 for x, then the only thing that changes is that over on this side, I've now plugged in a 1 into my parentheses skeleton. And now I have, again, a fraction multiplication problem for which we don't need to know a lot about fractions to carry out. What's 4/3 times 1 going to be? 4/3, because... Yeah. We have this rule for anything times 0 in arithmetic. We also have a rule for anything times 1, right? Those are the two easiest pieces of arithmetic to do, multiplication-wise. Okay, so then the question is, how do I find the point 1, 4/3 on the coordinate system? Think about that for a second. First of all, the fact that the x-coordinate of this point is 1 means I should start by looking where? Where should I begin my search on this coordinate system?
Look for the x-axis.
Yeah, so I'm going to start at the origin, then I'm going to go along the x-axis to where? I'm going to start here at 0, 0, and then move which direction? Right. To the right. Why right? Why not left? Because my x-coordinate's positive. Right. So I'm going to start, correct, rather. I'm going to start by moving to the right by 1 unit. And so this point, 1, 4/3, if we know nothing else about it at this point, we at least know that it's going to be somewhere along this vertical line here that's 1 unit to the right of the y-axis. So that's how we're going to locate it in the x direction. How about in the y direction? How do I find 4/3 in the y direction? The thing we know about 4/3 is that it's greater than 3/3. And since 3/3 is equal to 1, we know that 4/3 is going to be greater than 1. So our point is going to be somewhere north of this first grid line. here, right? It's going to be between 1 and 2 on the y-axis. It's less than 2 because 4/3 is less than 6/3. Right? So somewhere between 1 and 2. We don't have to be super duper precise with it. I don't want to get into a conversation of mixed numbers right now either. So I'm just going to kind of do the best I can to place that point a 1 unit of distance to the right of the y-axis and between 1 and 2 units of distance north of the x-axis. The point 1 comma 4/3 is somewhere right about there. And as promised, as advertised, as soon as we know 2 points, we can immediately sketch our line that passes through those 2 points. I'm going to try to do it as accurately as I can here. There we go. I didn't do the best job with that. Let me try and nudge it just a little bit. You get the idea. And so that line right there would then be a graph of the equation y equals 4/3 x. So our line's going to look something like that. I think that's corrected a little bit from what it was. Okay. Now the thing about choosing 1 for x is, on the one hand, it's super helpful for the arithmetic. On the other hand, it makes plotting that point kind of hard, right? Because our y-coordinate ends up being a fraction. But I want to sit with it for a moment because I want to talk about what the number 4/3 in this equation is actually telling us about this line. Does everybody know what the term is for the role that the number 4/3 is playing in this equation?
The slope.
It's the slope of this equation. How do we know it's the slope looking at the equation? Where do we find the slope when we look at an equation for a line? What is it about the number 4/3 in this equation that makes it the slope? What's it attached to?
Variable.
It's attached to the variable x, right. So it's what we call the coefficient of x in the equation. So 4/3 it plays this important role in the life of this equation that tells us something about this line. So here's a zoomed in slightly view of the graph that we just sketched. And when we did this problem a minute ago, we chose as the points to determine our line, we chose the origin, 0, 0, and then we also chose the point 1 comma 4/3, which is right about there. So those are the 2 points that we used to plot our line, 0, 0, and then 1 comma 4/3. And we just finished saying that the number 4/3 is what we call the slope. Of this line. Slope, by the way, is probably the single most important concept when you get to calculus. You're going to spend the first at least half of a semester, maybe the entire first semester, depending on which calculus sequence that you're in, talking about what the concept of slope does for you, not just for lines, but for any kinds of curves and any kinds of functions and equations that we can think about. Slope is a big deal. So this we're just kind of scratching the surface with, but the more that you can take away from our course an understanding of how to think about slope, the better that's going to serve you in the next 2 semesters that come after this one. So let's think just for a moment about how to understand the role that that number 4/3 plays. So one of the ways to think about it is that in order to get from the first point that we determined to the second point that we determined, we end up having to take 1 step to the right, followed by 1 step to the north. So I take a step to the right, and then I take a step up. Right? So the purple step and then the green step. Spencer? So the way that we set ourselves up here is we took 1 step to the right, so our x-coordinate went from x equals 0 to x equals 1, and then we took a step of a length 4/3 vertically, which was kind of a challenge because 4/3 is not a nice number that we can find on our graph paper, right? So my recommendation to you is when your slope is a fraction, you can make your life a little bit easier by taking the numerator and the denominator of that fraction and treating those as whole numbers. So taking the whole fractionaliness out of it, we can instead think about what might happen if let me ask the question this way. We'll see if it lands. Once we start at 0, 0, and we start moving along this line to the northeast, we don't cross through a lot of intersections of grid squares, right? We miss this little intersection here, we miss the intersections here, we miss this intersection there. Where is the next intersection that we actually hit? Looks like right about there is an intersection point. But then that one still doesn't occur at a whole number. It's a whole number value for y, but the value for x is between 1 and 2. So that's not a whole number coordinate point either. So we'll keep going. Still not an intersection, not an intersection, not an intersection, not an intersection. Here we go. Here's another intersection point. And this intersection point does have a whole number value for y, and it also has a whole number value for x. Halfway between 2 and 4, I should label it. So why don't we think about what it would look like to use that point as our second point? What are the coordinates of this point?
4 and 3.
4 and 3. Which is which? Which is the x and which is the y?
4 is the side.
Yeah, 4 is the y, so 4 units on the y-axis. So this is 4 units north of the x-axis. And 3 is the x because we're 3 units to the right of the y-axis. So that's nice because that's a point that has whole number coordinates. It's a lot easier to locate on graph paper. So my first question is going to be, how could we have gotten that point from the work that we did before? So the work that we were doing before, we were picking values for x. So we picked x equals 0, and then using the equation to determine the appropriate matching value for y. So what value for x would I have picked here if I were getting that point? I would have picked 3 for x. So what I tend to do, so this is my again, math expert blind spot talking, right? I think about this stuff for a living, so these are the kinds of insights that I try to pass on. What I like to do is I like to look at the slope and then zero in on the denominator. Here my denominator is 3. Not a coincidence that that's the value of x that I should pick if I want a nice whole number value for y. So if I pick x equals 3, then when I substitute that into my equation, y equals 4/3 x, when x is 3, now I do have a fraction arithmetic problem. I have to multiply 4 over 3 times 3. How do you multiply two fractions? Especially when that second thing is not a fraction at all, it's just 3. How do I understand 3 in a way that can turn it into a fraction, first of all? What's 3 as a fraction? Yeah, I'm just going to write it as a fraction whose denominator is 1. So now it's 4 over 3 times 3 over 1. Then how would I multiply those two fractions together? I saw a couple of dangerous hand motions going on the third row over there. And they're dangerous for the reason that the word cross multiplication gets burned into people's brains and it leads you astray. When we're multiplying fractions, one fraction by another fraction, you don't cross multiply. Don't multiply crosswise, multiply acrosswise. Multiply the numerators, multiply the denominators. Believe it or not, there's a place for cross multiplication, but it's not here. So what I want to do is multiply 4 times 3, getting 12. And I want to multiply 3 times 1, getting me 3. So when I multiply these two, what I really get is 12 over 3. What's 12 over 3 better known as? 4. Right. By the way, sometimes another way that people will rationalize that, no pun intended, is that we have a factor of 3 in my numerator. I also have a factor of 3 in my denominator. What can we do with factors that are common to the numerator and denominator in a fraction? We can get rid of them, cancel it. And so from there, we can just say the only thing that remains is 4 over 1, which is 4. So whichever way we slice it, when we put in a 3 for x, we get the whole number 4 out for y. So for me, when I'm looking at this equation, I'm asking what are some easy values of x for me to then be able to plot my x and y with? I would probably, myself, choose x equals 3 so that my y value could be a whole number, like this one. Let's return to the slope one more time. So the slope of this line is 4/3. And one of the places where we saw that slope turn up is we saw it turn up right here in our original formulation. So let me just write in here. One of the ways to interpret that, here's my slope, 4/3. one of the ways to close the loop on that is to say that the slope is how much y changes, how much y, the value of y changes, when x changes by how much? So how much did x change by here? Between our first 2 points, it was just 1 unit. So one way of thinking about slope is it's an answer to the question, if I increase x by 1 unit, what happens to y? Right? So in this example, when I increase x by 1 unit, y gets increased by 4/3 of a unit. And that's why the slope of this line is 4/3. By the way, where are my business management majors in here? So this masquerades, this has a name in business management. It's often called the marginal. So, for example, let's suppose that this equation we're modeling how much it costs to produce a product or something like that, right? Maybe my x-axis here is the number of units that I want to produce. Maybe it's measured in thousands or something like that. And then my y-axis is the cost of production. Let's just say. Then the slope tells us what's called the marginal cost, which is just the answer to how much to produce one more. How much does it cost to produce just one more unit? One more. And that one more is coming from this x changing by +1 unit idea. So when I say that slope is a big deal, this is one of the reasons that slope is a big deal, because this is how, in management context, you can use the calculus that you're going to learn a couple semesters from now. Talking about slope is an answer to a question, how much to make just one more? Or how much will my revenue change? How much additional money can I make by selling one more? How much additional cost will I incur by making one more unit? Those kinds of questions really drive how calculus is used in a business context. But just to complete this picture, in order to get the 4/3 popping out at us in this, we had to change x by just 1. But if we're using our 2 points that have whole number coordinates, in that context, we did things a little bit differently. How much did we increase x by in going from the first point to the second point here? What's the difference in x values? From there to there. Starting from x equals 0, going to x equals 3. That wasn't 1 unit, that was 3 units. And the difference in y values, going from y equals 0 to y equals 4, that was 4 units worth of change in y. So now our slope doesn't pop out at us as one of the numbers. Instead, the slope pops out to us as the relationship between those numbers. On the one hand, we saw 4/3 right here in our small triangle, right? This small, how much does y change when x changes by +1? But all I've done here is I've taken that small triangle and I've just stretched it out into a bigger triangle. But we can still recover the slope from this bigger triangle. All I have to do is take this +4 and this +3 and do what with them to get my slope? Just divide. Make the change in y the top part of a fraction, make the change in x the bottom part of the fraction. And that ratio, that relationship, gives us the slope. So just to put a final point on that. We can get the slope by taking this difference in y values, which is sometimes called a rise. It's how much do we rise on this graph? +4. And then taking the change in the x values, this +3. I don't have a lot of room to write here. We call that sometimes the run, the difference in the x values. And just dividing one by the other. And that's our definition of what it means to be a slope. It's the ratio of a rise over a run. is what we mean by a slope. So in all cases, what the slope is it's a relationship. When the values of x change, how do the values of y change in turn? Right? What's the ratio of the changes in the y divided by the changes in the